This is a Carboline production.
Zinc works very well to protect steel structures in corrosive environments. It works when you galvanize, it works when you metalize, and it works when you paint. So, why aren't these three methods understood more or less as equivalents? Partly that's to do with how well they themselves are understood. And paint is the odd one out. Our industry hasn't helped itself with all that secrecy surrounding proprietary formulas. That red bucket might as well be a black box. But today we're going to open that box because there's some things you ought to know about how these corrosion protection methods stack up against each other. And recent testing results are shedding new light on the oldest resin technology you've never heard of. Lab coats on, folks. I'm thrilled to have Kristen Blankenship back on the Red Bucket. Kristen is our product line manager for atmospheric coatings and this program's resident chemist. Kristen, welcome back. It's nice to have you here.
Well, thank you. I am happy to be back. It was a lot of fun last time.
Well, if you thought episode 17 was fun, then strap in because you're here to help us better understand zinc and its use in preventing corrosion. You're not here to do an 099 level lecture on zinc because instead we can just suffice it to say that its properties make it very useful to protect steel. We presume that anyone listening knows what the galvanic series is, or if they don't, they can type that into the search engine of their choice and get the picture pretty quickly. And then, from a corrosion protection standpoint, you can apply zinc to a surface in more than one way, and it will do what you want it to do. So, with that out of the way, Kristen, let's start with what you know about the history of zinc as a sacrificial material, because it goes back farther than I think we might realize, right?
Absolutely. So, my introduction to using zinc for corrosion protection was really in the past decade or so when I was working on weatherable coatings for steel bridges. And most of, the state of the art, if you will, is a three coat system that relies on something called a zinc-rich primer. So that was really my first introduction into the use of zinc. When I did some research in the course of writing some journal articles that I've done, I found that galvanizing, for example, has a couple hundred-year history. And believe it or not, thermal spray metalizing also has upwards of a 100-year history. Now, these techniques looked probably a lot different back 100, 200 years ago than they do today, but the concept is the same. When you apply zinc to steel, the zinc basically corrodes faster than the steel. And so you protect the steel and you sacrifice the zinc metal.
The exact same thing is basically happening with those little doodads of zinc on the hull of a boat. Those are there to sacrifice themselves in a highly corrosive environment instead of that environment eating a hole through your boat.
Exactly. I like doodad. Another term we use for those doodads is cathodic disbondment. We test for that, and we use those again because here's something a little bit mystical. The reason you can have corrosion protection of steel next to zinc, which those doodads, right? They're just on the boat in different places. They're not covering the entire hull. So how does that work? Well, that's the magic of electron flow and electron chemistry. So that's what we're dealing with is literally the flow of electrons. And so they are obviously microscopic, atomic level, and you don't have to have the zinc necessarily in contact with metal in that one spot for that galvanic cell to initiate. You need an electrolyte, usually it's water. Salt helps. Sometimes pH, a lower pH can help as well. And if you have those, then you have a vehicle for those electrons to move. So you can have your zinc doodad kind of far away from a spot on the hull and it still be protected. And so that same concept actually rings true in how we utilize zinc-rich primers.
So you don't need literal 100% coverage by zinc of the substrate, and the zinc can be intermittent, it would still perform its function?
Yes. And in fact, what we do in our testing of zinc-rich primers is we actually take a standardized scribe tool, because we're very standardized in the paint industry. And we take that tool and we cut into the coating system to expose bare metal. And that is to show in our testing that the galvanic cell is able to be formed and that corrosion protection can occur. So even though in the exposure of that test, you will have that bare metal exposed to salty water and moisture in the air, you will not have corrosion in that scribe, or it will be delayed for some time because you have zinc and you have the moisture, the electrolyte, to actually help those electrons flow, create that galvanic cell, and have the actual zinc oxidize and not the steel itself.
So let's walk through each of these corrosion protection methods: galvanizing, metalizing, and applying zinc rich primers. In each case, what's happening at the substrate?
What I'd like to start with is to try to reimagine these techniques in a more fundamental way, because currently for many people in the industry, they look at metalizing and galvanizing very different than using a paint system. And of course, a zinc rich primer is a paint. However, if we look at the fundamentals of what they're doing, which is utilizing zinc to galvanically protect steel, they're actually not so different. So I would like to kind of repurpose and reframe how we look at these from the fundamental of getting zinc on the steel, right? So if we're going to get zinc on steel, how can we do that? Well, one way, the oldest way, is we create a really big bath of very, very hot zinc metal and usually some type of acid. And that bath, we dip, anywhere from very small components to very large components of steel into it. And what happens in that process is there's actually a chemical reaction between the zinc and the iron. We call that a metallurgical bond. And so you actually get, in the chemistry terminology, that would be an ionic bond. So you form an inorganic complex between iron and the zinc. So that's pretty tough. It's pretty strong. You take it out, you let it cool off, and you've got a bunch of zinc on the steel. When you go to thermal spray metalizing, instead of a big bath with the zinc in more of an acidic solution, you actually utilize a spray gun. I've had some people say you could almost compare it to a welder or an arc welder, but you're using really high heat, flame almost, to take that zinc and make it molten, and it sprays onto the steel. Now, what's a little different here is that the steel has not been treated. It hasn't been, quote, pickled like you would see in a galvanizing process. So you're really just putting zinc dust and just kind of laying it down on the steel. So what we have to do in thermal spray metalizing is we have to use blasting to get a very deep angular profile so that we have a mechanical bond between the zinc and the steel. When it comes to zinc-rich primers, again, we're thinking conceptually about getting zinc onto steel. In order to get the zinc onto the steel, we use some type of resin system and solvent system, so some type of liquid. In the case of an inorganic zinc silicate, which is a type of zinc-rich primer that's used often and has been around for quite some time, it's usually some organic solvents and a resin system called silicate, and then you have the zinc in that. And so then what happens is you apply that to the steel. Usually you'll need a profile, maybe not as deep of an angular profile as you will with the metallizing, but you'll utilize that. You'll spray it on with just a standard spray gun, and then you will allow the solvents to dry. And over time, the silicate resin will actually cure with moisture in the air. And so now what you have is you have zinc on the steel, but you have zinc embedded in a silicate matrix. So you're getting zinc onto the steel, just like you are with metallizing and galvanizing, but now the zinc is kind of held in place by this rock-like resin system. And there's some real interesting phenomena that happen because of that, that make it very different in how it protects against corrosion compared to metalizing and galvanizing. When the zinc's on the metal, the zinc immediately starts reacting with the air and with moisture in the air. So it oxidizes. And theoretically, we believe that you go from zinc to zinc oxide to zinc hydroxide. Hydroxide comes in because of the moisture in the air. And then there's, of course, carbon dioxide in the air. And so then it goes even further and creates something called zinc carbonate. Zinc carbonate is a salt. We call it a corrosion reaction product. That product, that zinc carbonate, is actually insoluble in water. And it actually is a bigger molecule than zinc itself. So if you imagine zinc on the steel, those outer layers of zinc that are exposed to the atmosphere, creating the zinc carbonate, well, now you're starting to form a barrier. So you started with just zinc metal, zinc particles. And in the case of galvanizing, you actually have a gradation between zinc iron alloy at the surface of the steel, and then all the way up to the zinc air interface, you actually have close to 100% zinc. And again, it's because of that metallurgical bond, it's because of the galvanizing process that creates this gradation of a zinc iron complex that ultimately, as I said, results in 100% zinc at the surface. So you have 100% zinc at the surface in galvanizing. You have, of course, depending on your alloy, because sometimes in metalizing we'll do a zinc aluminum alloy, but for the purposes of the conversation, we'll just say it's 100% zinc. So again, free zinc, 100% at the surface. It immediately starts oxidizing, forms that zinc carbonate, and it sits there. It forms a barrier, but remember, it's just zinc metal. So if there's damage, if there's big rain cycles, heavy rain cycles, or wind, sand abrasion, eventually those outer layers of zinc will erode away. And of course, depending on where you are, that process can be more rapid, and in a lot of areas, it's going to be fairly slow. It's somewhat similar to what you see with weathering steel. Of course, it's very different. Weathering steel creates a really dark kind of purplish color of a patina, if you will. But again, there's not a lot of physical integrity to that. And so eventually it will start falling off and eroding away and exposing some of the zinc underneath that hasn't gone through that oxidation process. So then it just starts over. So again, it's a highly protective approach because that process takes so long. In the case of putting zinc onto metal using a paint vehicle, what you end up with is these zinc particles in the case of an inorganic zinc, in a silicate matrix. And I keep saying rock-like because it really is. It's sand, rock, whatever, silicates. These silicates over time will react with moisture and continue to cure over time. The outermost layers of zinc actually do get exposed to the atmosphere because unlike in a zinc-rich epoxy system, where the epoxy resin is covering a lot of the zinc, not all of it, but some of it, you actually have really good permeability of the atmosphere through that silicate resin system. And so that zinc that's in there is able to oxidize and form those zinc carbonates. But the zinc carbonate salts, they fill in the pores within the film. So you actually are forming a barrier in this rock-like matrix, and you're holding the salts in a little bit better. Now, some of you may be saying, okay, well, paint erodes and degrades over time. This is true for most organic coating systems. So think about epoxies, urethanes. They will break down over time with exposure to UV light. In the case of a silicate system, these materials are inorganic and they do not break down in UV light.
I'm recalling our conversations off the air about how comparatively little silicate resin technology has been studied.
Nobody talks about silicate chemistry. I mean, that's like, that's the next wave of research. Um, this is the oldest technology nobody knows about. And what I mean by that is it's the oldest technology that has no art. Nobody writes papers about zinc-rich primers. Like nobody's doing research on this technology. Like I say that in a bold way. It's compared to things like bio-based polyols for urethanes. You can find thousands of papers on that. But if you would actually try to find papers on zinc-rich primers, you go back to the 40s, 50s, and 60s because it's not a hot area of research. So
Hmm.
we're literally having to research it now. So things that we thought were true, like that you form a zinc iron silica complex, is that true? Is that really what happens? And if it does happen, can you call that a metallurgical bond? Just like we say galvanizing has a metallurgical bond. See, so we really just don't know a lot about it. Like like there's probably some guy that knows a lot about it, but he's either on his deathbed or dead. And so I mean I mean that's really where we're at. So
How do these methods compare in terms of adhesion? Like, how durable is that bond in each case?
in the case of adhesion over time, we know that galvanizing starts with really, really good adhesion because of that quote metallurgical bond. In the case of an inorganic zinc silicate system to metal, we have good adhesion initially, but over time it actually increases. And what we found with galvanizing is that over time it actually decreases. And the theory on that is that with galvanizing, you're actually, as we said, you're creating these zinc corrosion products, but they're just sitting on top of other zinc. They don't have structural integrity from any type of resin system or rock-like resin system like the silicates. So the way we measure adhesion with these systems is usually some type of pull, right? So we put a dolly on, we glue it on, and then we use a machine to kind of pull it off, and we measure the stress, the tension. So PSI goes down with galvanizing over time. It actually goes up in the silicate systems. At the end of the day, you need zinc on the metal. So if the zinc is eroding away over time, that's going to give you your life cycle. That's kind of how those all shake out in a comparison.
That sounded like a rather clinical and unbiased description of what the science tells us about comparative adhesion. But agree or disagree, clinical and unbiased would not be good ways to characterize how engineers and specifiers experience any comparison among these methods.
I would definitely agree with that. What I have seen in primarily in the bridge space, but I think it kind of it ekes out into the structural steel space at large, is this idea that we know zinc on steel protects against corrosion, and galvanizing and thermal spray metalizing are very straightforward, at least on paper, ways of getting zinc onto steel. When you put zinc dust in a paint or a coating liquid matrix, that's when things get a little bit tense and people get concerned and, well, what's the resin and who's it from and what all's in there? Can I know what all is in there, right? So a little bit of that black box. And that can be a little concerning, a little risky for some. So what I have seen is the adoption of metalizing as a technique has seemed to go maybe a little more smoothly than I would anticipate coming from the coatings world, where getting anybody to use a new type of coating technology requires years of many different types of testing, including real world, but also accelerated third party verification, you name it. So, one of the things that we've tried to do here is just look at performance testing standards and submit all of them to the performance testing. Now, we could all coat bridges or steel and just wait 50 years and see what they look like. But I don't know that any of us want to do that. And of course, it takes 50 years. And I hope I'm here in 50 years, but who knows, right? So, what we do in the coatings industry is we use accelerated testing, and we have, I don't know, you could maybe say many dozens of different types of accelerated testing. And then within each of those standards are, 5 to 10 different versions on the theme. So we actually leaned on a test standard called ISO 12944-9. And what it calls out, it's a cyclic test that goes from salt fog to UV exposure, so that sunlight exposure, and then a freeze-thaw cycle that gives some stress to the coating system. It's used and widely recognized around the globe. It's used a lot to specify and qualify coating systems for offshore structures, which would be the CX environment. So this is one of the most aggressive, corrosive environments that a coating could be in. And so we took some galvanized panels, some thermal spray metalized panels, and some panels coated with, in this case, it was actually a two-coat inorganic system. So we had that zinc-rich silicate type primer, and then we put a silicate finish, so an inorganic finish that allows for breathability. It allows for the moisture and the electrolyte to come through. It allows for continued cure of the silicate resin system so that you get the patina to form, but you also get that increase in adhesion over time. And we submitted all these systems to that ISO 12944 test, and we were not really surprised at the results. We saw that the metalizing did pretty well. It performed better than the quote state-of-the-art three-coat system, which would be a zinc-rich primer, an epoxy mid-coat, and a urethane top coat. We found the galvanizing was pretty good. You have to be sure that you get the right amount of zinc for the gauge of the steel that you're using. So we're kind of looking into that to make sure we did that as accurately as possible per the ASTM and AGA standards. But nonetheless, not so surprising, performed better than a standard three-coat system. And then we found with the two-coat inorganic system that it performed, I guess that was the surprise. It performed really better than all of them in the sense that we saw no corrosion at the scribe. So remember, we talked earlier about how we take a standardized scribing tool that cuts through the paint and allows metal to be exposed. And what we found after one round of this testing, which indicates roughly a 25-year service life in the most corrosive environment you can think of, offshore in the ocean, we didn't see a spot of rust. So that was interesting. And so we said, well, heck, let's just do it again. So we put it through again. Now, some people like to do the math and say, okay, so if I put it through 2 times and 1 time is 25, then 2 times is 50. I always argue with them that we don't know that because we've not tested the test, if that makes sense. We haven't tested the test to see if that is true and it's a linear relationship. But we put it through twice. Maybe that's 50 years, maybe it's 40, maybe it's 60. I don't really know, but it's more than 25. And we found, again, with the two-coat inorganic system, no rust in the scribe. We did see rust with the metalizing and the galvanizing. Again, still fairly good performance, especially with the metalizing. But we're kind of scratching our heads like, wow, metalizing and galvanizing are used all around the world every single day as long life systems, 50+ year service life. And people need to know what we're seeing with this two-coat inorganic system because it could be as good, if not better. And just to round out this conversation, we put it in a third time, and it's actually now in a fourth time. So we're just going to keep watching it go and seeing how far we can take it. But all that to say, the way that these types of techniques are adopted by different industries can vary greatly. And it's important, I think, that the industry look at a more fundamental approach to qualifying different techniques. Again, at the end of the day, we're putting zinc on steel, and how we go about it does matter. But the most important thing that matters is the performance.
I can't imagine anyone would disagree with you, and yet, in some sectors, and we've talked about roads and bridges, DOTs, coatings have a higher hurdle that they need to leap over in terms of standards and testing before they're qualified compared to these other methods. So, what's that all about? Like, why is it that way?
So there are standards that the galvanizing and thermal spray metalizing process relies on. The
Hmm.
standards are around quality and inspection. When you go to paint, we also have standards around quality and inspection. So, for example, quality, think of the surface prep standard, right? You got to be sure
Yep.
that you have this profile, right? We also have performance standards, and they just don't have them for metalizing and galvanizing. There's just, it goes back to the simplicity of metalizing and galvanizing. The way it's explained to an engineer makes sense because it's zinc and it's steel. and you're just putting zinc on steel. There's nothing else in the equation. Anytime you start talking about paint in a bucket, and I don't know what's in the paint. They tell me the hazardous things, but I don't know what else is in there. I don't know if it's going to work. I don't know if it's going to do what it said. But it all comes down to the fact that they're engineers. They're not chemists. So what's in that bucket might as well be alchemy. And so our industry over the years has relied on testing so that we don't have to tell everybody, including our competitors, what exactly is in the bucket. So we kind of have set ourselves up in the paint industry that that's just the norm. Nobody believes what you say. You have to prove it. You know, because it's zinc in a paint or a liquid system, it triggers all the testing that you would normally do for coatings. Metalizing and galvanizing, it's not expected because it's not paint. These DOTs have been galvanizing bridges and metalizing bridges, galvanizing more for a long time. And for the most part, they work. So what we're trying to do is just say, oh, by the way, there's this old technology that we were kind of not using the right way because we were putting epoxy and urethane over it. And it wasn't actually lasting as long as it could have without that. And when we did this testing, because that's what we do in paint, that's what I always say. In paint, that's what we do. We test, all these tests. We tested it and we said, well, my goodness, this is pretty good. And, you know, it might be as good or better than these techniques that you've used for a long time. So, Mr. DOT, so Mr. Bridge Engineer, we have an opportunity to give you longer service life, less maintenance, lower cost, less impact on the environment. And it's in a system that's been around for over 60 years.
Say more about cost and environmental impacts. Because we know cost is absolutely critical, it always will be. We know sustainability is becoming more and more so, and one of the major influences on the cost and ecological impact of each of these methods is the amount of zinc that each one uses relative to surface area and mill thickness. So, how do they stack up?
So if you think about metalizing and galvanizing, it's essentially 100% zinc. As I mentioned a little bit earlier, metalizing oftentimes will use an alloy with aluminum, upwards of 85% percent zinc to 11% aluminum. And of course, there's some zinc iron alloy. And then with the metalizing, you oftentimes are a little bit thicker on the metalizing. I'm thinking over 10 mils. That's all zinc or a little bit of aluminum. In the case of a zinc-rich primer, namely an inorganic zinc-rich primer based on silicate resin technology, usually you're in the 80 to 90%. Some products have 85%. Usually the more high-performing zincs are at 85. But at the end of the day, that 3 mil film, 85% of that would be zinc. So generally speaking, a zinc-rich paint system will rely on less zinc to protect compared to galvanizing and thermal spray metalizing. And up until very recently, I don't think most people gave much thought to that other than cost, right? But these days, the world is understanding the importance of being better stewards of our planet and our environment. There's a lot of tools on how to assess the impact of materials on the environment. Those tools are always getting refined and getting better. But currently, we have something called a life cycle assessment, and that helps us understand the carbon footprint of materials. So, zinc being a metal and a mined metal definitely has a carbon footprint. A lot of that has to do with the heavy equipment that's used to mine the earth to get these metals. And then, of course, the refining process, which uses a lot of energy to get down to the zinc dust that we need, or in the case of galvanizing or metallizing, the zinc ingots. So generally speaking, many of the zinc-rich primers are going to have a lower carbon footprint than these other techniques. And I know some of the zinc-rich primers, especially the inorganic zinc-rich primers, also have environmental product declarations. And also, and this is important, and I think it's going to be more important in the future, there is a federal highway prescription called Build America, Buy America. And that currently, I believe, is not completely enforced in the bridge market, but I believe it will be. And with that, you need a certain percentage of your raw materials in the construction project to be US based or US sourced. In the case of most zinc that's used in galvanizing and thermal spray metalizing, those ingots that I mentioned that are mined and then refined, they typically come outside of the US. We do have zinc mines in the US. That is true. But right now, a lot of the volume is outside of the US. In the case of zinc dust, which is what is used in the zinc-rich primers, that is sourced within the United States for the most part. Again, suppliers all around the world, but a lot of the products used in currently in the United States are sourced in the US. So when you have a system that's reliant on zinc, 85% plus, you're going to need that zinc source to be sourced in the United States to meet that Build America, Buy America requirement that, again, hasn't been fully enacted and enforced in certain market spaces, but we do anticipate that that's coming. So, generally speaking, if you can use your zinc in a more efficient way, keep your zinc on the metal by embedding it in a type of rock-like resin matrix that will not degrade over time. It allows the zinc to form that patina, creating that barrier that doesn't degrade with UV over time. You actually end up with something that's not only economically efficient, performs very well, but is also environmentally conscious.
I don't know that there's a better punctuation mark to put on the discussion than that one right there. So that's where we will leave it. The only other thing that we could do is ask Kristen the 4 questions, but we won't because she did that once already. Again, I refer you to episode 17. Give that a listen. She has strong opinions about hot dogs, and listeners will recall what Eric Zimmerman, a guest on our most recent episode, said about eggnog. So you've come here for the coatings, but you stay for the hot takes about food. Kristen, thank you very much for joining us today. This was great.
Thank you. And all of us are going to have to give you the 4Q someday. So we'll have a special episode for that. Sound good?
It's only fair.